Stars come in a lot of different types, 7 main types to be specific, and they're classified by temperature. The blue giants burn the hottest at over 30,000 Kelvin, while the coolest red dwarfs burn below 3,500 Kelvin. Let's start at the top. Class 0 stars are the largest and hottest stars, and they're also some of the rarest. Their surface temperature is over 30,000 Kelvin. That extreme temperature is what gives them that bluish white color. These stars can be 1,000,000 times more luminous than our own sun. Because of this, their lifespan is cut short. Our sun will have a lifespan of around 10 billion years, but Class 0 stars might only last for a few million. They're incredibly rare and short-lived, but they're so bright that some of them are actually visible from Earth. They usually go out in supernovas, but sometimes they leave behind a neutron star, but we'll cover that later in the video. Stepping down in temperature, we have Class B stars. These range from 10,000 to 30,000 Kelvin. Still bluish white, but slightly more common than Class 0 stars. 860 light years away, Rigel is a bright supergiant star in the Orion constellation. It's a Class B star that swelled up to massive proportions as it aged. Despite being that far away, it's still one of the brightest stars in the night sky. If you put Rigel in the sun's place, it would reach almost to the orbit of Mercury. Like Class 0 stars, they don't have a long lifespan, typically burning out in the tens of millions of years. Then we've got Class A stars. Temperatures of around 7,500 to 10,000 Kelvin, giving them a white or slightly blue appearance. These are some of the most visible stars in the night sky. Sirius is the brightest star visible from Earth, and it's also a Class A star. These stars have lifespans ranging from hundreds of millions to sometimes billions of years. Still shorter than our sun, but it's getting closer. Fun fact, Sirius actually has a white dwarf orbiting it. So while Sirius itself is still burning bright, looking at its tiny, dead comparison gives us a glimpse into the exact kind of stellar corpse Sirius will one day become. Class F stars sit around 6,000 to 7,500 Kelvin. A little bit hotter than our sun and looking closer to it with that yellow-white color. These stars are fairly common and have lifespans of a few billion years. Procyon is the brightest star in the Canis Minor constellation, and it is a Class F star that is just starting to expand. Now these stars are decent candidates when looking for habitable systems. They're hotter than our sun, which pushes the habitable zone further out, but they burn through their fuel faster too. A few billion years is a lot, but it might not be quite enough time for complex life to really get going. Class F stars are the middle child of stellar classification. And now, we're back to our own solar system. Class G stars or yellow dwarfs are what our sun is. Surface temperatures between 5,000 and 6,000 Kelvin. Interestingly, despite being called a yellow dwarf, the sun actually appears pure white when viewed from space. That familiar yellow look is mostly our atmosphere scattering away the blue light, but either way, these stars have a lifespan of around 10 billion years and the sun is about 4.6 billion years old, roughly halfway through its life. As we talked about earlier, the sun is actually in the top tier of stars when it comes to size and brightness, and that specific sweet spot of stability and energy is what allows complex life to develop and evolve over billions of years. The closest star system to us is Alpha Centauri, and it contains a Class G star, Alpha Centauri A. So our nearest neighbor is basically a slightly larger version of our own sun. The system also includes Proxima Centauri, a red dwarf that's technically the closest individual star to us at 4.2 light years away. So Class F stars burn too hot and die too fast. Class G is where we live. But there's actually a class of star that might be even better for life than our own sun. Class K stars or orange dwarfs are cooler, sitting at about 3,500 to 5,000 Kelvin, which gives them that bright orange color. They're more common than stars like our sun, and astronomers are increasingly favoring these as candidates for habitable systems. They can burn for 15 to 45 billion years, much longer than our sun, which means way more time for potential life to develop and evolve. They're also stable enough that even planets orbiting fairly close won't get constantly bombarded with solar flares. Class K stars are probably the best bet for life in the universe, despite us not ending up near one. And now, literally the coolest main type of star. Class M stars or red dwarfs have surface temperatures below 3500 Kelvin. They're tiny, dim, and red. They're also the most common type of star in our galaxy, making up roughly 70 to 75% of all stars. That's actually the main reason the sun outranks roughly 90% of stars like we talked about at the beginning. It's not that the sun is special, it's that most stars are just really, really small. Red dwarfs also have a mind-boggling lifespan. Some have a theoretical lifespan of trillions of years. The current age of the universe is only 13.8 billion years, so red dwarfs are still basically infants on a cosmic timescale. TRAPPIST-1 is a red dwarf relatively close to our solar system and has several Earth-sized planets in its habitable zone. The problem with red dwarfs is that their habitable zone is extremely close to the star itself, which means planets are often tidally locked. One side is constantly facing the star and the other remains in complete darkness. They also give off powerful flares that could strip atmospheres from any nearby planets. So while they seemingly live forever, they're not the best candidates for life. Those are the 7 main classifications, but sometimes the universe throws us a few curveballs. Here are a few that don't fit neatly into the main types but are too interesting to skip. Remember those Class 0 stars that go out in supernovas? When a massive star, something with 8 to 25 times the mass of our sun, runs out of fuel, it sometimes leaves behind a neutron star. Take everything that made that giant star massive and crush it down into an object roughly the size of a city but with about 1.4 times the mass of the sun. A single teaspoon of neutron star material would weigh around 1 billion tons, roughly the weight of Mount Everest. Some of them spin hundreds of times per second. The fastest known ones clocking at 716 rotations every single second. They emit massive amounts of gamma rays and X-rays, and in some cases, the neutron star has such an extreme magnetic field that it gets classified as a magnetar. That's a special type of neutron star with a magnetic field roughly 1,000 times stronger than a typical one, powerful enough to tear apart atoms from thousands of kilometers away. Now, on the complete opposite end of the spectrum, we have white dwarfs. This is what our sun will look like once it dies. When a star like our sun runs out of hydrogen fuel, it sheds its outer layers and leaves behind a dense stellar core roughly the size of Earth. That core just slowly cools over billions of years with no fuel left to burn. Remember that white dwarf orbiting Sirius from earlier? That's the exact same fate waiting for our sun too. And then there are brown dwarfs. These are basically failed stars. They form the same way stars do, but never reach the mass needed to sustain regular hydrogen fusion. Without that fusion, they have no lasting energy source, so they just slowly cool and fade away over billions of years. Some of them actually cool down to the exact same temperature as a pizza oven. They're sometimes given their own spectral classes beyond the main 7, labelled L, T, and Y, but most people don't count them as true stars. And that brings us right back to where we started. The universe is filled with stars that are too hot, too volatile, or just flat out failed. When you look at the sheer chaos of giant blue stars exploding and red dwarfs blasting their planets with radiation, our boring little yellow dwarf suddenly doesn't seem so bad. It's the perfect, stable cosmic engine that gave us the chance to exist in the first place. If you enjoyed this video, subscribing is the best way to keep these videos coming, and if you want to go further, the Patreon link is in the description. Supporters get early access to videos, a vote on what gets made next, and their name in the credits. Either way, thanks for watching and I'll see you in the next one.